Evet, günaydın arkadaşlar. Ee, dün bir oops, sorry. Let's switch to English. Well, we started yesterday with a case study, and we have studied the algorithm or the pseudocode for the topological sort, and we tested it using black box testing. Uh, uh, and I gave you two exercises about the topological sort. Let me show it to you one more time. Okay, the two exercises were to prepare the test cases, observing the optimizing and extending principles, and the second exercise was to draw the control flow graph for the topological sort and to find the cyclomatic complexity. Okay, now let's uh, start with a second example. But before that, I would like you to send me these test cases and the control flow graph, um, if you may. Uh, and I will start with the second exercise then. I sent you my email so that you can send the solutions for these two exercises. I will now I will start with the second exercise, the insertion sort. Um, well, the insertion sort you again remember from the data structures class, but the code is here. The code to insertion sort is here, and I have numbered the specific statements, and I also gave codes to the conditions for the decision structures, both in the argument of the for loop and in the while loop, and also here in the if structure. So now I would like first to specify the or I would like you to apply the category partition method to this for black box testing again. And this is another example. This is another case study for us to apply black box testing. Okay, what may be now? What may be or how will we apply the category partition method to insertion sort? As you know, the first step to category partition method was to specify the input categories for this insertion sort. What do you think may be the input categories? What may be the program parameters or problem parameters in this code in insertion sort? What do you think? I would like you all to make your suggestions through the chat panel to me. Okay. Uh, mhm. Okay, what would be, well, you all see that we have an array here, right? So, since we have an array, I think the parameters of the array, each parameter of the array is another input category, right? So, for example, an answer is number of entries to sort. So that corresponds actually to the size of the array, right? Size of the array is an input category. What is another one? Type of the elements that we're going to store in the array, right? Exactly. So an answer is the array A, but what from this array A? The size, for example, is an input category. What other? The size of the array, the type of the elements, maximum and minimum elements in the array, perfect. Exactly, and the positions of the maximum and minimum elements. Exactly. Okay, great. So, uh, well, I think we have six different categories already specified. These are the size of the array, type of the elements, maximum and minimum elements in the array, and their positions. Great. So let's look at the input categories. These are the input categories you have mentioned, you have suggested, and these are the input categories. Let's go with the second step then. What are we gonna do for each of these input categories in the second step? I want to hear each of you to tell me what the second step is. Okay, I am getting now some answers, and these are all correct. I would like others to write their suggestions too. Thank you very much. Okay, well, if you write your suggestions, then I will see that you're actually following the class. So I would very much appreciate your participation. Um, yes, the answer is to establish equivalence class for each of these input categories. Um, All right. So, what do you think? What do you think may be the representatives for each equivalence class in the size of the array? What may be the representatives for each of the equivalence classes in the size of the array category? Perfect. Perfect. Very nice. Çağla, Kevser, Elif. Well, these are nice answers. Great. Okay. Frat, your answers are also correct, but I would like a more comprehensive answer. Like, for example, an invalid integer. and the intermediate representatives too. For example, 1, 2, 5, 100, right? Uh, Positive integers, yes, but like you have to specify what typical integers would be. Like, for example, 0, 1, 3, 5, 10, 100, or and something greater than 100, and also invalid integers, invalid answers are also, or invalid inputs are also necessary, like -1, for example. Um, yeah, but in general, you understand what's going on, and these answers are mostly correct. How about the types of elements? What would you say for the types of elements? What are the representatives for each of the equivalence classes? Yep, okay. Well, mostly the answers are correct, but don't forget each representative, each representative, you're adding to the set of tests for each input category contributes to the number of test cases in a multiplicative way. Well, you have to multiply each of these cases with each other. So every single equivalence class you add to your test cases, or you add to your uh, uh, you wanna include in your tests contributes to the number of test cases in a multiplicative way. So that means it affects the number of test cases uh, essentially. Okay, so but yeah, the mostly the answers are correct. How about the max element value and min element value? What may be these numbers? For max and min element values, what would you say the equivalence classes would be? Well, well, yes. It is it you cannot say from 1 to 100 these would be 100 different integers, and that would be too much, Salih. So you have to specify several numbers, and these numbers might be like between maybe 5 to 10 elements at most, as I said, because they contribute to the number of test cases in a multiplicative way. Uh, yep, okay. Well, Kevser, these are these are too little number of equivalence classes. Like, for example, -5 is fine to represent the invalid equivalence class of invalid input. 95 is fine too, but you have also to enter several other numbers, like, for example, uh, something greater than 100 or 200, something between 1 and 100, etc. So there should be 4 to 5 test cases. Yes, for example. Yep. As a matter of fact, the max and min values, element values, may be the same. The equivalence classes for them might be almost the same numbers or equivalence classes. Okay, perfect. How about the position of max element? How about the position of max and min elements, both E and F? These should be some array indices, right? Yes. Perfect. Yep. Okay, great. Let's look at these equivalence classes and compare them with what you have suggested. So maybe I should also include a negative number in the size of arrays, and I also uh, for the types of elements, I included 4 cases: max and min element values, a large negative, I said -1, a typical one, a 1, and a large positive. I said position of max and min elements at start, something at start like 0, 1, something in the middle, at the end, something towards the end, and some equivalence class that will represent some number that will represent the equivalence class for out of bounds. Okay, so that makes also in position of max and min elements 4 cases each, and here 5 cases each, and 4 cases here, and 6 cases for the size of the array. Maybe this may be 7 too, or we, instead of 2, for example, I can put a -1. That would, of course, be a better. That would, of course, be a necessary inclusion of the of a sample number for invalid size array sizes. And well, assuming that these are the numbers, these are the numbers of equivalence classes at each input category, uh, what would be the total number of test cases for the black box testing I need to apply? Well, of course, don't miss it. Don't forget for each of these two two input categories, I have 5, and for each of these input categories, I have 4 cases. So that would be 5 times 5, 4 times 4 times 4 times 6, and this gives me, no, this is 6 times 4 times 5 times 5, or 25, and 4 times 4, or 16. So this gives me 16 times 25 times 4 times 6, right? Are you sure? 25 times 16 is 400, times 4 is 1600, and times 6 is 9600. Yes, yes, 9600 is the correct answer. Please multiply them again. Yes, yes. C and D represent actually 2 different input categories. So we have here 5 cases each and 4 cases each. Okay, so this adds up to 9600 different test cases. All right, you can see it here. And uh, to optimize, okay, well, these are too many, of course. So what are we going to do? We are going to optimize the number of test cases. And what does it mean? We cover for each invalid class a test case, and for each other equivalence class, that is for each valid classes, by at least one test case. All right, so this is the optimizing principle, and we have to apply this to reduce this infeasible number of test cases into an optimized one. Okay, and then if we have, if once we do this, if we have too few test cases, then we can extend them using the extending principle, which tells us that we have to cover each parameter in a test case in the set of pairs, triplets, etc., until all parameters are covered once. Well, these are the two test case examples: 101 integer for array size 101, integer for the type, minus 5820 for the minimum element value, 7101 for the maximum element value, 2 for the position of the minimum element value, and 47 for the position of the maximum element value. And here we have another test case example, 3 for the well, this is rather a test case for the boundary values, 3 for the size, array size, float for the type, 0 for the minimum element value, 100 for the maximum element value, 2 and 3 for the positions of min and max elements. So, well, this is still a valid test case, but it is around the boundaries. Okay. So these are the two test cases for the two possible test cases for the black box or yes, black box testing. So now I would like you to draw for me the flow control graph of this insertion sort. So I am showing you here the insertion sort so that you can draw the control flow graph of this insertion sort. Then we will look at you will be able to compare yours with mine, and then we will see how we will compute the computational complexity and find the independent paths. All right. I'm giving you now 5 minutes so that you can draw the control flow graph. All right. Through the chat panel, I wrote you what you need to do, so you understand it, all right? To draw the control flow graph, you have 5 minutes, and then send a picture of it to me through my email. All right? Okay. How is it going? Did you draw it? Yes. Yes, Çağla. Okay, thank you. All right. Now let's look at the control flow graph. That's fine. Now please focus back on the class, on the slides. Um, this is the control flow graph. All right. I please don't send any. It's 9:06 now. Don't send any more emails. Okay. Please look at the control flow graph because I'm showing it to you. So this is the control flow graph. Okay. Well, we have again. Let's look at the code. Here we have 1, 2, 3, 4, 5, 6, 7 statements. All right, 7 statements, and 3 of these are conditions. So, okay, we have uh, we have starting with I equal 2. Let's see. Starting with I equal 2 in the for loop, that makes 8 statements. All right. So we have, including this, we have 8 statements, and including the begin and end nodes, we have 10 nodes in the graph. Okay. Let's count it again. 1. Okay, well, let's start here. 1, 2, 3, 4, 5, 6, 7, and this is the final one, 8. And including the begin and end nodes, if we're going to count these edges too for edges, if we're going to include these 2 edges that lead us from begin and to the end node, then we're going to have 10 nodes. We're going to have 10 nodes, all right? So I would like you now to compute the computational complexity for me. And I told you that 8 plus 2 is equal to 10 nodes, what we have as far as the nodes are concerned. So I would like you to count the edges and then compute the computational complexity. I'm sorry, cyclomatic complexity. I'm sorry. Please compute the cyclomatic complexity after you have counted the number of edges. As you remember, the cyclomatic complexity was equal to the number of edges minus the number of nodes plus 2. I wrote it down here in the chat panel. Please count them again, Kevser. Okay. Well, Berk, I'm waiting for others to answer, so that's why I'm not answering you. But yeah, let me write it down for you. I said the number of nodes is equal to 10, right? Here, these are the numbers for the nodes. Okay, 1, 2, 3, 4, 5, 6, 7, 8 nodes plus begin and end nodes. So it adds up to 10 nodes. So all you need to do is to count the edges and then subtract them from node number and add to 2. Okay. Well, the correct answer is 4. All right. The correct answer is 4, and this is oops, sorry. Edges minus nodes. Cyclomatic complexity is equal to edges minus nodes plus 2. Well, the number of edges is 14. I'm sorry, 12. Okay. Minus, we have 10 nodes included with begin and end nodes, plus the constant 2 is equal to 4. Okay, so the cyclomatic complexity is equal to 4. Let me count the edges. 1, 2, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And this is 12. Oh, well, somehow, did I miss something? 1, 2, 3. Okay, this is the 12th one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and this is 12. Okay, and I actually marked them using these red stars here. So 12 plus 2 minus 10 gives us 4. Now, what is this 4? What does this 4 tell us? What does the cyclomatic complexity give us actually? What does it tell us? What is this 4? What is this number of 4 for this algorithm, for this code? Well, number of paths, number of linearly independent paths. All right, great. Number of linearly independent paths. Now, I would like you to note, for your sake, for your own, the linearly independent paths. What are the linearly independent paths? I would like you to find out what these paths are, and then I will show you what they are, and you can check whether you did correctly. You have another 3 minutes for that, to find out the linearly independent paths. You have to, of course, you know all that you have to show the paths using the as a sequence of nodes. Which one? Okay. Which one do you mean? Okay, Ömer has a question. Ömer Faruk Okumuş has a question. Why didn't we count the one that is not marked? You're talking about an edge, I guess. But which is this? Is it this edge here? Is it this edge? Ömer, I am showing to you. Is it this edge you're talking about? Okay, well, this is, I have answered you here using this text. This is not marked since it is the continuation of these two edges, all right? So that's why I didn't mark it, because that would be one too many if I had marked and counted it, all right? Because it is the continuation. It's like you can assume it like this. This goes, continues, and ends up here, and this one goes, continues, and ends up here. Do you understand what I mean? Okay. So, did you determine the linearly independent paths? You don't have to write B. You don't have to start with B. They all start with B. So I don't want to. Okay. Well, that doesn't hurt. Well, I equal 2 is marked with 8. It is the 8th node. So you can start with 8 instead of writing I equal 2. Well, you have the numbers here. The nodes are marked, Fırat. The nodes are marked. For example, this node is 8. This node is 1 here. This node is 2 here. Maybe you didn't see them. Okay, perfect. Let me show you so you can. Well, not 815. I guess 81S is what you want to say. 5 is up here. 5 is up here. 81. Okay. Let me show you the independent paths. These are the independent paths. So check yours out again. And if you have any questions, please do ask me your questions. All right. Check them out and ask me your questions. But okay. Mm-hmm. Sure. What do you mean by separate edges? What do you mean by separate edges, Frat? I, Frat, I will. Okay, all right. Okay then. Well, let's take a 10-minute break, and I will see you again at 9:30. Okay? I will see you again at 9:30. Let's take a 10-minute break now. Okay. Uh, well, thank you all who sent me the email for your exercises. Um, well, do you have any questions to start with? Do you have any questions? I was going to send. I'm sorry. I was going to show you the independent paths here. This is this here is 8-1. Okay, I'm not counting the begin and end notes. So 8-1 is the first independent path. Okay, this here, if the first conditions result is true, then it becomes 8-1-2-7-1, 8-1-2. I'm sorry, 8-1-2-3-7-1. Okay, 8-1-2-3-7-1. Let's look at the second one. 8-1-2-3-7-1. Okay, and 8-1-2-3-4. I'm sorry, 8-1-2-3-4-5-3-7-1. Let's look at it. 8-1-2-3-4-5-3-7-1. And the last one is 8-1-2-3-4-5-6-3-7-1. So the last one is 8-1-2-3-4-5-6-3-7-1. Okay. Okay. For Çağla, let's repeat the first one. 8 and 1. And from begin, we go to the end note, to the last note directly. Okay, Çağla, did you get it now? Okay. Well, let's go to the second example, if we may. This is the cyclomatic complexity for the insertion node, and let's go to the topological sort again, and let's see the exercises you did. And for those who didn't do the exercises, I will give them another 5 minutes, as a matter of fact, so that they can complete now the exercises and send them to me. The exercises were: prepare the test cases, observing the optimizing and extending principles, and then draw the control flow graph and find the cyclomatic complexity. So, okay, what are the given these equivalence classes in the categories? Can you give me two test cases? Okay, can you give me two test cases for these categories that observe, well, not two test cases, but several test cases actually, that will correspond to the optimizing and extending principles? And I would like you to draw the control flow graph of this here. Okay, so please draw the control flow graph for this and give me several test cases that will follow optimizing and extending principles. All right, so for each of these exercises you have 5 minutes. So together this will give you 10 minutes time, 10-minute time, so that you can complete the exercises. Then we will look at the control flow graphs and find the cyclomatic complexity and find the independent ways, and then you can compare these with yours. All right, so I'm giving you now 5 minutes for each of these exercises, so you have 10 minutes. Okay. Uh, how is the how is the how is the control flow graph coming? Did you draw it? Did you draw it? Okay. All right. Let me give you another minute, and then we'll be done, and we will be seeing the flow graph. No, you don't need to send me the test cases, just the control flow graph. Just the control flow graph. Okay, now. Well, I will be showing you the control flow graph of topological sort. So I'm not accepting any more emails after 9:49. Okay. So this is the okay. This is the exercises. I'm sorry. This is the control flow graph. All right. This is a little more complex than the insertion sort, this topological sort control flow graph. So we have here, as you see, we have here 12 nodes. Again, the nodes are marked with numbers 7, 8, 9, 11. We have 12 nodes, as also shown in the algorithm itself. We have 12 nodes here shown. Well, to compute the cyclomatic complexity, what do we need to do? So n is equal to 12 here. Oops, sorry. n is equal to 12 here. What is E equal to? And the E, the number of edges, actually the edges are marked with the lowercase letters. All right, so you can count them. From starting from A up until S. So we have altogether 19 edges. So now you can uh, uh, compute the cyclomatic complexity. Can you write what is the cyclomatic complexity? Can you send me from the chat panel? What do you think it is equal to? Okay, as you know, the cyclomatic complexity formula is the number of edges minus the number of nodes plus 2. Okay, and you have to, okay, if you count A and S, which uh, leads us from the begin node to the first statement, and S leading us from the last statement to the end node. If you count these two edges, then you have to count the begin and end nodes in the number of nodes too. So if you count A and S, then you have to count B and E too. Without B and E, we have 12 nodes. If you count B and E, begin and end nodes, we have a total of 14 nodes, all right? So, Çağla, actually I'm talking to you. If you count A and S, which makes up 19 edges, then you have to count the begin and end nodes too. Then the number of nodes is not 12, but 14, okay? Okay, so the cyclomatic complexity is then equal to 7. 19 edges minus 14 nodes, 5 plus 2, the constant in the cyclomatic complexity formula, gives us 7 as the cyclomatic complexity. So what does that mean? What is 7 now for this control flow graph? What is 7 for this control flow graph? What does the cyclomatic complexity tell us? Yes, exactly. Thank you, Kevser. It is the number of the independent paths. It is the number of the independent paths. Again, let's find for this control flow graph the independent paths. Now this will take a little time, so I give you another let's say 5 minutes for writing down your independent paths, and then we will see if what you found is actually correct, comparing it with my with independent paths I found. Okay, yeah, you have 5 minutes now. Okay, I think you got an idea about what the independent paths are. Now let's find them together. Oh, thank you. Great job. All right, thank you. Um, Thanks to all of you. Okay, let's now see what some of them may be. Uh, 1, 2, 1, 2, 5, 10, 12. So this is the shortest independent path of flow. Now let's show you another one. 1, 2, 5, 10, 11, 12. This is another one. Okay. Now let me show you another independent path. 1, 2, 5, 6, 7, 5, 10, and 12. Again, this third one again. 1, 2, 5, 6, 7, 5, 10, 12. Okay, let's show you a fourth one. 1, 2, 5, 6, 7, 8, 9, 7, 5, 10, 12. Let me show you another one. 1, 2, 3. Oops, sorry. 1, 2, 5, 6, 7, 8, 7, 5, 10, 12. Another one. 1, 2, 3, 2, 5, 10, 12. Another one. 1, 2, 3, 4, 2, 5, 10, 12. So I don't know. I think I showed you 6 independent paths. There are 7. So let me show you all of them here. Okay, these are the independent paths. These are the independent paths. Well, the first one I showed you, the second one I showed you here, 10, 11, 12. This one, 1, 2, 5, 6, 7, and then 5, 10, 12. I showed you 1, 2, 5, 6, 7, 8, 7, 5, 10, 12. I showed you. This one I showed you too. 1, 2, 3, 2, 5. This one I showed. Yeah, I showed you all of them, I guess. Each of these 7 ones, and I also have for you. I also have for you some dependent paths and how they can be shown, by which independent paths they may be shown. For example, 1 to 5, 6, 7, 5, 10, 11, 12 can be shown using this one and this one. Okay, this is a dependent path, and it can be shown by the linearly independent paths 2 and 3. Okay, this one, for example, is another dependent path, and it can be shown by 2 and 4. Okay, this is another dependent path. This can be shown by 2 and 5. And finally, this is the longest path, and it can be shown using paths, independent paths 2, 5, and 7. So now, well, this is I think a good exercise from the complexity viewpoint too, to show you how a control flow can be drawn from a code, and how its cyclomatic complexity can be calculated, and how the independent paths, linearly independent paths, can be found, and what the why the dependent path, or I'm sorry, what the dependent paths are dependent upon as far as the linearly independent paths are concerned. So this gives us, I think, a good enough view about the white box testing. So, do you have any questions from these subjects? Do you have any questions? Do you have anything that you don't understand? How this control flow graph is drawn, how the independent paths are extracted, how the cyclomatic complexity is calculated, etc. Do you have any questions? Yep, I'm listening to you, Malik. The okay, the number of the okay, wait, Malik. Well, dependent. Do you mean these dependent paths? Okay, all paths other than the independent paths are dependent. All right, and for example, look at the first one. 1, 2, 5, 6, 7, 5. Okay, 1, 2, 5, 6, 7, 5. So this first five nodes are in the third one. The only thing that is missing is 11 in the third one, and it comes from number 2. All other numbers, 1, 2, 5, and 1, 2, 5, they are the same here in the second and third path. 10 here, oops, sorry, 6, 7, 5 is the same here at the third one. The only thing missing here is 11, and 11 comes from the second path. All right. Okay. Now there is a question from Ömer. Is there any simple way to produce independent paths? Well, by looking at the flow graph, you can find the independent paths, but it is not automatic. Okay, it is not automatic. Well, there is no other way to find out the independent path. You have to by finding the cyclomatic complexity, you find the number of the independent paths, but then you have to turn back to the control flow graph and check them each out manually. Okay, Ömer? Okay. Uh, well, this is it is Ekram. It is from the code that you extract, and okay, there are statements which we show by small circles, and there are decision structures like this, for example, like the 3, like the 7, like 8, and like 10. Okay, these are each decision structures, and we show them using these routes. Well, that's, I don't know, this I think this is German, but yeah, using these yellow square-like things. Okay, I'm sorry about that. And these are the decision structures. That means where the yes or no edges go out. Okay, and we have for each ekran for you. We have, let me, okay, we have in the lecture notes for week 10, we have the structures for each of these single statements, or for the decision structures for the for loops, while loops, do while loops, while do loops, etc. So you can check them out, and you can draw these graphs using these structures that we have discussed in the week 10 lecture notes. Okay, you're welcome. Okay, any other questions for this case? Okay, I see that you don't have any questions. Then I will make a simple start with the software cost estimation today in the remaining 10 minutes, and then I will continue with that next week. Okay. Please don't do that. Please don't draw. Okay. Well, software cost estimation is the next chapter we are going to talk about, and we will cover here. We will introduce here the fundamentals of software costing and pricing. We will describe the three metrics for software productivity assessment. We will explain why different techniques should be used for software estimation. And finally, we will describe the principles of the algorithmic cost estimation model, COCOMO. Okay. Well, this is an interesting name back from the 1980s, and there is also another version of this proposed, which is COCOMO 2. Well, we will talk about that too, and we will, at the end of this chapter, we will be able to calculate the software productivity of any software product, of any software product development process, and then we will also be able to use the algorithmic cost modeling for software costing. Okay, we will also be able to compute project duration and staffing needs for any software development project. Okay, the fundamental estimation questions are: how much effort is required to complete an activity, how much calendar time is needed to complete an activity, what is the total cost of an activity, and these three questions are fundamental software cost estimation questions. All right. So I would like to know the effort that is required to complete an activity in a software development project. How much calendar time is needed to complete an activity in the software process, and what is the total cost of an activity. Okay, these are the things that I would like to estimate while I develop a software product. What are the software cost components? Hardware and software costs, travel and training costs, effort costs. This is the dominant factor in most projects, the salaries of engineers involved in the project, and social and insurance costs, their social and insurance costs. Effort costs must take overheads into account. So this effort costs should cover costs of building, heating, lighting, costs of networking and communications, and costs of shared facilities, for example, library, staff, restaurant, etc. So this is a comprehensive analysis of how we should establish the software cost considering these different components about software development. Okay, let's talk about the costing and pricing. How do we make estimates? They are made to discover the cost to the developer of producing the software system. There is not a simple relationship between the development cost and the price charged to the customer. So it depends on many factors. Okay, so there is not a simple relationship between the cost of development and how the customer will be charged. There's a broader organizational, economic, political, and business considerations that influence the price charged. Well, what are the most important factors that affect the software pricing? For example, the market opportunity. A development organization may quote a low price because it wishes to move into a new segment of the software market. A development organization may quote a low price because it wishes to move into a new segment of the software market. Accepting a low profit on one project may give the opportunity of more profit later. The experience gained may allow new products to be developed. So for the market opportunity, I can say that well, you may be putting a new product, new generic product, for example, new software product for use for many customers. So if there are several competitive organizations that are also about to put this into the market, then you might like to be the first one that puts such a product to the market, because if you put your product before all others do that, then you can be the first one that has put such a product to the market. And even if you put a low, even if you accept a low profit for this first step, the experience gained may allow you to develop new products, and it also will give you the opportunity of more profit in the coming sales. All right. So this is market opportunity is important for the software pricing. So you may want to keep the price low, so that your product is well known by the customers. So this brings you more sales in the coming in near future, and that except in a low profit now, you will gain, or you will get the opportunity of more profit in the coming sales. So this is so much for market opportunity. If you like, let's stop here and let's start talking from the software pricing factors in the next coming week. Okay? I will see you next week then. Thanks for the participation. I will see you next week.